So as you can see here, this is one typical example of a silicon and silicon dioxide interface. So here, as you can see here, this is a silicon dioxide interface. So this is taken from one research group's journal paper, and in this high resolution TM image, you can find some dots, bright dots. So here, maybe I can use different colors. So you can identify those dots. Those dots are corresponding to silicon atoms. So this is one silicon atom, and this is another silicon atom. So when you have a look at their arrangement, you can find in this way. There is a certain silicon atom, for example, let's say this guy. After that, you can find someone slightly away from this one. Yes, here you can find it. Also, you can find another one which is located just in between them and a little bit above this guy. Yes, here you can find this one. And if we go further, exactly the same amount of this upward direction, then you can find another one. Yes, this is found. You can find certain structures shown here. So these silicon atoms are regularly placed in this way, and just to copy and paste this unit pattern, you can entirely make this silicon substrate. So this is due to the periodicity of silicon atoms. This is crystal. And when you have a look at this upper part corresponding to silicon dioxide, so maybe it is a little difficult to find any kind of regularity or periodicity. So can you find it? So these bright ones are corresponding to still atoms, but their arrangement just looks like randomly distributed. So it is difficult to see any kind of order inside it. So you can clearly distinguish these two different parts, crystalline silicon and amorphous silicon dioxide. And what is the border between these two materials? So can you recognize the border? So this line is not the natural image, but drawn by these researchers, and they think that maybe up to this point, yes, this is corresponding to the regular silicon crystal structure, but above it, well, it is difficult to say crystalline structure is maintained. So they say that this is the boundary. And when you have a look at this part, then actually you can see that this is corresponding to this level. You can see that they have the same level, but here we have one further atomic layer corresponding to this guy, and they means that the authors of this research paper says that up to this point this is crystalline, and above it, well, it is difficult to see the crystalline structure. So although how can I say, the determination of the border between perfect silicon and silicon dioxide is somewhat arbitrary, not clearly cut cut by a knife, but as you can see, well, it is true that there is a certain deviation. So for example, in this part, relatively in the lower part we can have the border, and in this part we have a relatively higher place, the border, and here we have a certain border, and there is a sudden increase, and here we have a change. So now you can understand the interface between silicon and silicon dioxide is not perfectly clean because they are made of silicon atoms by stacking them up. So up to here, okay, I will stop here, and after that, yes, this is a silicon dioxide. And in this part, we say that up to here, I will just stack silicon atoms, and above it, here we have silicon dioxide. And once again, here we have a certain border. So how can we characterize this roughness? So the surface just does not look like this. I mean that if we go to this random sample, it's not like this, up, down, up, down, up, down, up, down. If our system or our interface really looks like this, then this has also a certain order. So every second atomic position, we have up and down. Well, this is a well-ordered one. However, the distribution or occurrence of this up and down is really random. So we have no idea what will happen if we have a certain level. Then in the next level, it will be still flat or going up and going down. So can you just predict the next position? Actually, it's not. Point is, this, at least this shape is not as random as drawn here. It's not that much frequent. So every time it is up and down, up and down, up and down. It's not. So you can easily understand there is a certain kind of a characteristic length. Okay, maybe 2 or 3 atomic lengths, maybe the surface looks flat, and after that there can be a certain increase, and after also a few atomic steps, so it can be just smooth, and where it is now changed. And also again, here we have a certain changing. So I'm not saying that every 3 atomic distance, after that it goes up, and every 3 and also it goes down. It's not written in that way, but what we can expect is there is a certain expected range of flatness. Well, after a few atomic layer, maybe there can be a certain probability to have a up and down and up and down. This roughness can be observed. So since this is really random, so it is difficult to just to predict the exact number. Instead of that, for this stochastic quantity, we typically use autocorrelation function to describe it. It is simply given as this way. So, well, let's just say I have a position taken as the origin, then starting from this value, then if I go to a certain amount, so written as here r, so in this case let's say that this is origin and distance is r, then what is the product between this level and that level? This product is calculated. So let me just say a little bit more. Let's just say that this is the flat level, and I say that at a certain position we have roughness corresponding to this amount. Of course, when you just make the average of this roughness, the average value will be exactly 0, because this roughness is taken as deviation from certain surface from its average level, so its first order average will be just 0. However, if we just make a product between this one, so say that this roughness and another position, distance is r, when we make a product between them, then it can contribute to certain level. For example, let's think about this one. If our system really have a certain property like this, every atomic layer we have 1, minus 1, 1, minus 1, say that 1, minus 1, 1, minus 1, 1, minus 1. And if we just calculate autocorrelation function when the distance is 1, then what we will get is like this. Here we have a positive 1, and here we have a negative 1, and here we have a negative 1, 1, 1, minus 1. Then every position, from every position, we will have a certain contribution to this autocorrelation function. So using this autocorrelation function, we can find a certain quantity. When the distance is distance between 2 points are given as r, then how much they are correlated. So say that if we have, for example, perfectly, this is the average value corresponding to the roughness 0, and say that we have a constant roughness far away from this average value, and let's say the distance is taken as a shorter than its average distance for changing this roughness. Then what will happen? If you take these 2 points, one point and another point, they will contribute a positive number. And if you take another distance r, also it will contribute to positive number. You know, if you have quite a long trail of these positive numbers, then if they share the sign, then all of them will contribute to positive contribution to your autocorrelation function. And let's say that when we have a negative function, negative contribution, it occurs only when we have a certain sign change here. In this case, we will have a negative contribution to our autocorrelation function. So simply speaking, let's assume certain characteristic length level. This is the shape of our roughness, and if we take quite a short distance r, take the difference only between this short distance or short distance, then maybe this autocorrelation function will give you quite a high value, because actually these two values are the same, and we just have square of this surface roughness. However, if we use very large value for our distance, say that distance is given as this one and that one and this one and another long distance, then what will happen? So there will be no guarantee that we have still positive values for our autocorrelation function. Simply speaking, by calculating autocorrelation function, when r is smaller or shorter than certain characteristic lengths, we can expect that autocorrelation function will give a certain positive value. And if we have the distance much longer than our characteristic length, we can expect that autocorrelation function will diminish and close to 0. So usually what we do is just to model this autocorrelation. Experimental autocorrelation function can be described either Gaussian profile or this is the exponential function. Please have a look at these two forms. They share the same property. When we have very small r values, when distance is taken as quite a short value, you can see that just square of a certain expected roughness value. However, if we go to long range correlation, when R goes to infinity, and both cases we will have a quite a small vanishing autocorrelation function. It means that actually one point here and the point far away from this one point separated by distance r, actually they are not correlated at all. Autocorrelation function means that how much these two coordinates are correlated in terms of their roughness. Simply speaking, if we just consider two neighbors, maybe they have same roughness. And if we consider 2 points far away from each other, then maybe they are not completely uncorrelated. They are completely uncorrelated, so autocorrelation function vanishes. And the difference between this Gaussian function or exponential function is how rapidly they are vanishing to the zero. You know that this is a Gaussian decays much faster than exponential function. So it really depends on experimental data. So experimental data is taken, and in order to describe their shape, sometimes researchers try to fit their result with Gaussian or exponential, but it depends on your data. So simply speaking, anyway, it is certain that there really exists the roughness between silicon and silicon dioxide, and from the viewpoint of one electron, for example, if you have an electron located here and it try to move in that way, then what will happen? It feels that this interface is changing, and it really affects the movement of our electron located nearby silicon dioxide interface. That's the reason why if we have mobility of electron, then when x is close to 0, so interface between silicon and silicon dioxide, our expected mobility is much lower than the mobility at x equal to infinity, not affected by silicon dioxide interface. Okay, so this is one typical reason why we have a position dependent local mobility concept. Of course, I'm not saying that this is quite rigorous in terms of physical accuracy. Actually, we have a better explanation about the electron gas, but I think that this is a little bit beyond the scope of this course. So if you are interested, then please keep your study. However, in this lecture, I think that it is enough to show you the rough surface. So maybe your electron is quite close to the interface. It feels that rough interface, and that rough interface works as an additional scattering mechanism to reduce the electron mobility. So now you understand this effective mobility is something like this, mu n. However, this is although this is average mobility, but it's not like this. This is not the definition of effective mobility. The definition of effective mobility is we are currently using our electron density as a weighting factor. So we just point out the average electron mobility felt by our electrons. Of course, what you can do is, for example, you can use hole density as your weighting factor. So also you can use hole mobility. Then you can also find the effective mobility for your whole gas. But in our atmosphere, usually electrons are charge carriers, so we do not calculate the effective mobility of holes. That is not calculated. Of course, that is calculated for our P MOSFET, of course. So anyway, so after that, they measured effective mobility. And effective mobility can be measured as a function of gate voltage. And general trend is if we apply higher gate bias, then there is a tendency to have lower mobility. Effective mobility is reduced. So this is not a good news, because if we wanted to use our transistor, usually what we do is apply very high gate voltage corresponding to VDD, and we wanted to use that electron channel as a charge conducting layer. So unfortunately, compared with the position like 0 volt, so here we have relatively higher electron mobility, but unfortunately our actual mobility for our real application is somewhat lower than the mobility which can be expected in our lowly biased case. So this is not a good one, but this is the real life. So our mobility is not as high as shown in our textbook. Usually we have lowered values. So although I have told you this one in the previous lecture, I wanted to stress once again. If you have a look at, or if you read research papers, sometimes researchers say that, oh, we have a very good material, and this material has quite a high intrinsic mobility. So maybe it is good to use this new material for our transistor channel material. But please be careful. The real mobility you have to use is not mobility shown here. The mobility is important when you apply high gate bias. In this case, always your mobility is reduced by some unwanted reality. So you must consider the real value you can imagine or you can expect from your real technology. So anyway, so let's say that certain foundry A, and let's say there is also foundry B, foundry C, blah blah blah. In the worldwide sense, we have so many foundries. So all of them are fabricating their own MOS transistor. Each of them is doing their best. I wanted to make a very good device as much as possible. So at the time, and still true. And previously, certain researchers just to collect data from foundry A, foundry B, foundry C, something like that. At the time, it was from USA, America, also European. At the time, there were so many European semiconductor companies, also Asian companies. Yes, there was also Asian companies, maybe at the time, mostly Japanese companies. And they collected all data from these companies, and they tried to draw mobility as a function of gate voltage. Of course, they have different threshold voltages, different oxide thickness, different substrate dopings. So therefore, there is no hope to have any kind of universality. However, amazingly enough, researchers have found that instead of this gate voltage, if we just switch it to a new or different independent variable called as effective electric field, then now, amazingly enough, independently fabricated MOS transistors, all of them share the same behavior. So you can find it here. This is at the time their best data. So you can see that here we have effective electric field instead of just gate source voltage, and here we draw effective mobility, and you can see that in this case actually they have different substrate doping. For this is a M MOSFET and this is for P MOSFET. As you can see, although there are 6 different samples, but they just looks like just one single line. And here you can see there are 5 different samples, but you know they look like just one single sample data. So how can we have this kind of behavior? It is because although they have, all of them have made their own devices, but the inside the system we have only one single physics. Here we have a silicon dioxide, and this is silicon. And now I'm drawing the conduction band. So although they are fabricated by different fabs, but when we draw their conduction band profile, always when we have a certain given effective electric field, their conduction band shape are the same. So since they all share the same physics, their generated electronic state are the same. That's the reason why, although they are fabricated from all different companies, but they share the same form. So this is called as universality. Wow. So although it is not important who made it, if they did it correctly, then we will get this universal mobility curve. So that was the consensus, and maybe late 80 and 90. So that was the situation. So mobility, we never exceed this given universal mobility. If you make your transistor with conventional silicon, then you cannot expect the mobility as high as 1,000 square centimeter per volt second. You never expect it. So that was the previous case. Okay, so let's come back. So people really loved this concept. Oh, it gives certain feeling. Oh, we are doing a certain kind of universal thing. So we are now doing our best job. So at the time, if a certain guy makes MOS transistor and measure the effective mobility and say that our mobility value, actual mobility value is far below than universal mobility, then what does it mean? Oh, we are losing the game. So actually we must increase the mobility, because all of them, all of our competitors are matching the universal mobility curve. Well, what is the problem? Maybe there is a certain contamination in your device. That was the situation. So people really love this concept, and however, in order to match this beautiful curve, we have to introduce this effective electric field. Then what is this effective electric field? This effective electric field is average electric field, once again, felt by our carriers. So means that, let me just explain it a little bit further. Here we have silicon dioxide and silicon. And now let's say we have electronic gas. Yes, usually electronic gas just looks like this. So here nearby this silicon dioxide interface, we have a lot of electrons. After that, the number of electrons or density of electrons are decreasing quite rapidly. let's ask this question. So what is the electric field felt by the really surface placed electrons? And here we have very small number of electrons just below this electronic gas inversion layer. Then which one has a higher electric field and which one has a lower electric field? Of course, everybody knows that since there is a gate terminal, so there is a strong electric field. So we can expect that we have a maximum electric field at silicon dioxide interface. Here we have a maximum electric field. After that, inside this inversion layer, we have tons of negatively charged electrons. They just reduce the electric field as much as possible. So when this is over, then now we have much weaker electric field. So even though the physical thickness of this inversion layer is just a few nanometer thick, so it's not that thick, so this is quite thin. However, inside that short range, we have significantly different electric field. So what is the average value of our electric field felt by overall electron gas? So what they do is like this. Just takes this one. Simply speaking, the electric field at this position can be expressed as QD divided by epsilon silicon. And this interface part can be written as QD plus QI divided by epsilon silicon. So as you can see, the difference comes from electronic contribution. At surface, all of our electronic charge contribute to the electric field, and at the starting point of our inversion layer, there is no contribution from our inversion charge. So then what should be the correct weighting factor for inversion charge? So if electrons are uniformly distributed, then maybe this half will be the best one. And if electrons are distributed non-uniformly distributed, maybe this weighting factor can be a little bit different. So that introduces a lot of complication for definition of effective electric field. But in the case of electrons, there is a consensus that we have to use half to make this effective field. Then by using this effective field determined as QD plus half of QI, now you can have this beautiful universality for your effective mobility. Additional topic is P-MOSFET. So here you have a P-MOSFET, and in the case of a P-MOSFET, if we just define our effective electric, if we define our effective field just like N MOSFET, actually there is no universality. So people love universality. However, in the case of a P MOSFET, we cannot get the universality. So what they did is, just to play with this number, weighting factor. This weighting factor is related with the distribution of electrons or holes, and they played with this number, and they have found that happened to be 1/3 restore the universality. So why we have one half and 1/3 for this weighting factor? Well, there is a certain theory about why we have to have a half and third, but I think that is beyond our lecture contents. So anyway, now people understand for P MOSFETs, we have to use 1/3 as a weighting factor, and after that we will get quite much beautiful universality curve. That was situation in 80 and 90, and so it means that when you have a look at a certain given electric field, effective electric field, so always electron has a much higher mobility compared with our holes. So that's the reason why when you study your microelectronics course or other kinds of circuit related courses, you always say that, oh, your MOSFET is more conductive than your PMOSFET. So therefore, in order to match their drivability, you have to introduce a little bit wider PMOSFET to match the drivability. And the factor is usually taught as number 2 or 3 because, you know, here we have a certain difference, and this difference is corresponding to number 2 or 3. So that was the situation we had in the previous time. And so if you are looking at Professor Tower's book, it's a second edition. There was no discussion about strain effect on mobility because the second edition was written in early 2000, and this third edition, the latest edition, is maybe around 2022. I'm not that sure exact ending number, 2000 something in second edition. At that time, stress engineering was at its infancy, but now currently we are heavily relying on the strain effect. Simply speaking, this universality holds for certain material called as relaxed silicon. Relaxed silicon means that we do nothing to our silicon substrate, just to leave it there, and it shows this kind of a performance. But people nowadays are trying to introduce a certain stress on our silicon substrate, and it has been found that by applying the strain, we can actually get electron mobility much higher than the universal curve. So it sounds like a cheating. So, well, this is a universal behavior, but how can you increase the material property called as mobility? It is related with this one. So by applying certain stress, now silicon has different atomic distance between two neighboring atoms. So our band structure is originated from the atomic placement. So since we have make a change in our atomic configuration, so band structure itself is affected by that strain effect. So by changing this atomic configuration, we can intentionally increase or decrease the mobility of our silicon material. So nowadays people are using in that way. Instead of this relaxed silicon, so now we wanted to use strained silicon. Of course, all of our hope is to increase the mobility. What we wanted to do is have this line and have this line. Wow, that will be the perfect one. So they have made a certain theoretical and experimental job, and they have found that, okay, for both of our P MOSFET and M MOSFET, we have knobs to increase their mobilities. In order to increase electron mobility, we have to make certain ones like this, as shown in the next slide. In order to increase our electron mobility, for example, so let's say that this is X and Y, and please regard it as our top view. We have a vapor, and we are now looking it from top, and this is a vapor surface. And in order to increase our electron mobility, actually we have to make an extension or expansion of our silicon material. So this is usually called as a tensile stress, and when silicon occupy wider volume than a relaxed one, of course, actually volume expansion itself is not that important. Important one is directional expansion. So if we introduce expansion along the transport direction, then we can increase electron mobility. So simply speaking, if we introduce so-called tensile stress to our electron channel, then we can increase our electron mobility. How about holes? In the case of holes, also we can increase hole mobility. But in order to increase hole mobility, actually what we have to do is shown here. Actually, let's say that this is the direction for our electron or hole conduction. Then along that hole conduction direction, we have to actually compress our material. This is called as compressive stress. If we apply compressive stress, then now hole mobility can be increased also significantly. So maybe you feel certain contradictory feelings about these two ones. I'm saying that in order to improve electron mobility, actually we have to introduce a tensile stress. Means that we have to make it expand it. And in the case of a P MOSFET, actually we must compress it. So, in our CMOS technology, at the same time, we fabricate N MOSFET and P MOSFET. So how can you do that at the same time? They are completely the opposite case. So what we do is locally, when we try to make N MOSFET, we apply uniaxial, not this biaxial, but uniaxial tensile stress is applied to our N MOSFET. At the same time, for P MOSFET, we apply uniaxial compressive stress. So how can you do that? So this is just nanometer scale, several nanometer or micrometer scale chip. However, at a certain position, we apply compressive stress, and at a certain position, we apply tensile stress. So this is actually the magic by our fabrication engineers. So therefore, we can locally introduce local stress to individual MOSFETs, so they can be improved. So please note that this is a verbatim taken from Professor Tower's third edition. Overall, the VLSI industry has utilized strain to gain about 10 or 20% N MOSFET performance and 50% or even higher for P MOSFET performance. So means that after introduction of this stress engineering, so although MOSFET's performance has been boosted a little bit, but it is more important to get quite a high boosted PMOSFET performance. So nowadays, the mismatch between MOSFET on current and PMOSFET on current is not that high, not like a factor of 2 or 3 taught in our circuit design books. Usually, maybe it is really comparable, just several 10% difference in their own current. Okay, so this is, although this is a quite important one, so I think that I have to wrap up this discussion right now and move to another one. But please be careful. This stress mobility engineering has been the driving force to improve the device performance for quite a long time. Even nowadays, when we try to make next generation device technology, this stress engineering is the number one criterion whether one technology is available or not. For example, let me just give you one short story. Nowadays, people try to make a certain architecture called as a CFET. In this CFET technology, say that this is a deep substrate direction and this is a front side surface direction. So usually what we do currently is fabricate the MOSFET and fabricate the PMOSFET in a same plane, front side, and just tie them up. So this is the typical case. But in the case of this CFET technology, what we try to do is fabricate a certain FET and introduce another FET on top of this bottom tier one. This is a bottom tier, and there is a top tier, and they have different polarities. So quite naturally, we can ask ourselves this question: what should be the bottom and what should be the top? For example, P MOSFET and N MOSFET. Or we can try to fabricate the other way around, N FET and P FET. If we ask ourselves that question, then of course we have to find out the best solution to maximize the performance. And which one maximize the performance? The answer is this guy is much better than this guy. What is the main reason? It is related with strain. In the case of this P-FET bottom case, we can apply sufficient stress to our P-FET, PMOSFET. So PMOSFET performance can be maintained. However, if we switch to this architecture, P-FET is located in top tier, and there is no sufficient way to apply sufficiently high strain to our P-FET. So PMOSFET performance dropped down drastically, so we cannot get any performance gain out of this structure. That's the reason why everybody says that P-FET is located in bottom and N-FET is located in the top. So you know that stress engineering nowadays the top priority when we consider this kind of one. So now let me give you the final remarks on the strain. Even when we consider new materials like 2D channel materials, so people at the first time, people try to introduce 2D materials, and they are believed that to have a sufficiently high mobility. But problem is when it is made as the channel, once again their mobility is degraded. So compared with the silicon, there is not that clear advantage of a 2D material when it is actually used in the channel material. So nowadays, what researchers are doing currently is also introduce stress to our 2D materials. So, for example, MOS2, not just mere MOS2, but strained MOS2s are being investigated, and it is found that actually we can get huge improvement in its mobility. So since we can play with strain and play with mobility, maybe that is an interesting research topic for further technology development. So why I'm saying this mobility topic continuously, it is because once you select your device or your material and architecture, then maybe the mobility is the most powerful knob to improve your device performance. So mobility is quite important, so you have to understand the importance of mobility and some factors affecting the mobility. And now let's go to our next topic. So short channel effect. Short channel effect is, I think that this is quite important to understand modern transistors. Up to now, we have considered long channel device. Long channel device, how long is it? So infinitely long. So then what is the practically infinitely long? If you are talking about nanoscale devices like 10 nanometer node or 20, then 1 micrometer long device can be regarded as long channel device. But let's say previously we had 0.5 micrometer technology. In this case, 1 micrometer long channel is not a long channel device. It should be regarded as a short channel device. So please, there is no absolute condition whether it is short or long. It really depends on the technology. Compared with the minimum size you can have, if your actual device has much longer than that, then we can say that is a long channel device. However, if your device is comparable with your shortest length device, then you have to say that that is a short channel device. And nowadays it becomes even more important, because nowadays in most state-of-the-art device, the most advanced devices, actually there is no long channel device. Unfortunately, we cannot fabricate a long channel device any further due to the fabrication procedure. In order to make a long channel device, first of all, we have to expose quite a long channel. However, previously it was done within just a planar silicon substrate, but nowadays for the most advanced technology, it is just hanging on the air. So if you have quite a long channel device, actually the channel itself is not straight, but due to gravitational force, there is a certain curvature in it. And if we have also different silicon channels, and they are actually interacting each other. So nowadays it is almost impossible to make 1 micrometer long device with state-of-the-art device. There is no such kind of device at all. So actual device should be always treated as a short channel device. Then the behavior of your short channel device is much different than your long channel device. So that's the reason why we have to study especially the short channel device from now on. And now I'm showing quite a short device whose how can I say, whose channel length is 50 nanometer. But please be careful. If we make 50 nanometer device with state of the art technology, then already 50 nanometer is quite a long channel, because the minimum length nowadays is actual length scale is about 15 nanometer or slightly shorter. So compared with this one, 15 nanometer would be already 3 times longer than the minimum length scale. So it can be regarded as a long channel. But I'm saying that the technology shown here is just a planar MOSFET technology. So 50 nanometer is always already the limit of this technology. So we can treat it as a short channel device. And let's make a comparison with 1 micrometer long device, which is extremely long in this case. So I have drawn them in the same scale. So you know, this guy is a 50 nanometer device, and this guy is a 1 micrometer long device. Now you can feel that compared with a short channel device, long channel device is really long. So now you can see that when you have these two different devices, which one is more conductive and which one is less conductive? Obviously, you know, this guy, this short channel device should be much more conductive, because our ID expression always have mu n Cox W over L factor in front of it. So this is effective mobility. More or less they share the same parameter. Oxide thickness, this is, yes, this is also shared. And W over L, for given W values, their difference comes from 1 over L factor. So since they have 20 times difference in their length scale, so you can also expect maybe roughly 20 times higher current for this device. Okay. Then this is the result. So here short channel means that 50 nanometer, long channel means 1 micrometer. How about your feeling about them? So we are now having quite a low drain bias, and you can see that the difference is really huge. In this case, we have about 0.3 milliamp, and this is much lower than that. So this is just 10 or 20. I'm not quite sure. So this is corresponding to 50 microamp. So the value would be 10 or 20 microamp for this long channel device. So when you make a comparison, you can find that at least there is 10 times one order of difference in its drain current value. That is quite much expected. However, I wanted to ask you once again more important question. Well, increase of drain current is expected, and please try to estimate the threshold voltage of these two devices. They share the same technology. They have made on the same wafer lot. So what we expect is, since they are just breeded in one place, they should have the same threshold voltage. But when you have a look at their threshold voltages, so I made an individual graph for them. You know, this is I'm not quite sure. Okay, this is long channel one, and I guess that this is short channel one. Much higher current. So same data, just separately drawn. And please try to estimate the threshold voltage. One way to estimate the threshold voltage is just to draw these input characteristics at low VDS value. How low is it? This is 50 millivolt. Yes, this is good. 0.1, this is also okay. Or sometimes people use 10 millivolt. Yes, it's also okay. Anyway, please use low VDS value and draw your ID as a function of your gate voltage. Then you will have this brown curve, and after that, please try to find out the steepest slope from this graph. Where can you find the steepest slope? So for example, here your slope or normal curve looks like this. This is just moderate. And when you go to here, then slope becomes a little bit more steeper. And where can you find the steepest one? Maybe you can find here the steepest one. So find out the point where you have the steepest one. Actually, this slope is corresponding to what? It is corresponding to your transconductance at linear case, GM linear case. From this GM value in linear mode, so make just a normal line, and you will get certain intersection point between your normal line and this horizontal line. Then you will have a certain voltage, and threshold voltage is estimated around that intersection point. Of course, there is a certain correction using half of VDS value. However, in this case, this VDS value is quite small, so this correction is not that important. So anyway, when you have a look, and it has its own name, this is GM, called as GM max method. So just to point out the position, the voltage where it shows the maximum transconductance. From that maximum transconductance point, try to make a linear approximation, and you will find the threshold voltage. And if you follow this GM max method, then you can find that, okay, this is corresponding to the threshold voltage of our long channel device. Maybe it is around 0.45, I guess that between 0.4, 0.5. And when we go to our short channel device, we did it once again. And what we get is the value slightly lower than 0.4 volt. Well, maybe you can say, well, 0.45, 0.30 something. It's not that big deal. No, it is actually quite a big deal. So we have differences in threshold voltage when we just reducing the channel length. When we have a long channel, we had well-defined threshold voltage, but by introducing shorter channel, actually our threshold voltage is reduced, even when we apply quite a low drain bias. Okay, so let me just show you very important graphs. So this kind of graphs is quite important. So maybe you will see later this graph or similar graphs quite many times if you are working in this semiconductor field, especially as a device engineer. The x-axis is channel length. When you reduce channel length, so this value is corresponding to long channel value, and of course this value is corresponding to our short channel devices. And what happens if we go to short channel device? That is the typical way of drawing certain quantity, whether threshold voltage, div, or any kind of quantity, is drawn as a function of effective length or channel length. And what we usually want to have is just a flat line, not affected by the channel length. We wanted to have the technology which is quite insensitive to the channel length. That is our ideal case. However, as you can see, unfortunately, threshold voltage is affected by the length. So here, when we have a long channel, we have a well-defined threshold voltage. And when you go to short channel, even when you go to this value is almost identical to the long channel value. But if we introduce a further, even shorter transistor, actually threshold voltage goes down. Well, please be careful. From now on, please concentrate. Here we have two different curves. One curve is corresponding to low drain bias, and another curve is corresponding to high drain bias. So you have to understand these 2 points. One, usually this kind of behavior, so the reduction of a threshold voltage is usually called as threshold voltage roll off. So usually people call it in this way. This roll off itself occurs even for low drain bias and high drain bias. That is one observation. So this roll off itself does not depend on drain bias voltage. So I mean the roll off exists even at zero drain bias voltage. But second point is, however, roll off is more significant here when you apply higher drain bias. I mean that even when you apply quite a small one, you have it. But if you apply even higher drain bias voltage, then you will have even severe roll off. That is these are 2 points we have to understand. So usually people say that short channel effect is related with DIBL, drain induced barrier loading. That's correct. That is the most important one. However, even without high drain bias, still that happens. So I will explain it. These 2 points one by one. The first one is the one occurring at relatively low drain bias, even at zero voltage. And please note that this happens not only for MOSFET, but also for PMOSFET. That happens when we draw threshold voltage as an absolute value. Always absolute value of our threshold voltage is now reduced. Same happens for our MOSFET and PMOSFET. This is the case. Here you can see that the condition where drain voltage is 0 volt. There is no effect, no additional effect of drain voltage. Drain voltage itself is 0, and this graph just make a comparison between your long channel device and short channel device. This is a 50 nanometer and this is a 1 micrometer. And drawn quantity is conduction band energy. So conduction band energy EC is drawn. And where can you find the source? Yes, this is the source. And since this red curve is corresponding to short channel device, after short distance, now drain comes. This is the drain of our short channel device. In the case of a long channel device, we have a long way to go. After that, after 1 micrometer long channel, after that we have the drain of a long channel device. Point is, when we make these two devices, they have all the same parameters, only geometrical length, channel length is different, and conduction, please have a look at this conduction band minimum energy. So you know that for long channel device, this is the maximum energy of our conduction band. It is above 0.4. And when you have a look at this lead curve, what is the maximum value? The maximum value would be about 0.36 or 37 volt. So there is a certain lowering of EC value just to introducing short channel compared with previous case. So even though we don't have any kind of a drain effect, but already the maximum potential barrier is lowered. So what happens? In this case, from the viewpoint of our electrons placed in this source side, previously in the case of long channel device, it was very high, but by reducing just channel length, its high ceiling is a little bit lowered. Just a little bit lowered. So does it matter or not? Please note that our current conduction is exponentially dependent on this barrier height. Since barrier height is slightly reduced, so now our current can be increased exponentially. So please note that the difference is about, this is corresponding to 50 millivolt. So this difference is about 2 times kVt over Q. So what you can expect is that there are several times higher current conduction than this long channel one. So you can easily understand that is one effect we can expect from this one. Then maybe you can ask me this question. Then why do we have this barrier lowering? We have not introduced any kind of drain voltage, but what happens? Please have a look at this long channel behavior. In order to consume the structural difference between source and channel, at least we need certain amount of length scale. Also, in order to consume the geometric difference, we need a certain difference. Starting from this energy level, go to that level, it's not abruptly changing. We need a certain transition region. But when we make our device much shorter than this transition region, even before reaching to this maximum value, actually our band profile should go down once again. So that's the reason why now when we have quite a short distance, then we have to have lowered maximum energy. So simply speaking, the junction between our source and channel, or junction between drain and channel, they need a certain length scale to have our ideal channel region. However, if we reduce our length scale too much, then there is no, how can I say, no enough length scale to reach the maximum value available for our long channel device. That's the reason why we have a relatively shorter one, and this is called as charge sharing. So for example, the charge at this part is solely determined by only our gate terminal. However, the charge in this part is not fully controlled by gate voltage, gate terminal voltage, but also affected by our drain voltage. As you can see, this EC value itself has certain intermediate value between gate determined value and drain determined value, so they have some intermediate controllability on this part. So that's the reason why when we have this lead curve, can you say that this at this point the charge density is solely determined by only our gate terminal? Actually not. It is controlled by partially by gate, partially by drain. Also similar happens for this point. This point, gate and source plays at the same time simultaneous role to control the charge density. So that's the reason why this behavior is called as charge sharing. Up to now, this is related with low drain bias case, and the next Monday we will keep our discussion on the important quantity as a double. So what happens if we apply even higher drain bias? Okay, thank you for your attention and see you next Monday.